Okay, in this video I want to talk about L'Hopital's rule, and it looks like La Hospital, but it's not, it's L'Hopital, and indeterminate forms. And this is sort of a strange section to come at the end of the content, so to speak, but it is a way to analyze limits algebraically without limits that we couldn't analyze algebraically before, or analytically I should say, previously. So let me motivate this by giving you an example. So if we take the limit as x approaches 0 of sine of x over x, we have a problem. And the problem is that when we try our tools for analyzing limits, and maybe it's worth going back over them real quick. Direct substitution is the first thing you try, right? You plug in the value, and into the function, and if there's a value that comes out the other side, then that's your limit. Right? If that doesn't work, then we said, well, then you try doing something algebraically. So maybe it's factoring the top and the bottom and seeing if something cancels out, thereby getting a function that doesn't have that situation of 0 over 0. Okay, so 0 over 0 is what we call an indeterminate form. It's sort of nonsensical. And so if you try direct substitution and you try algebraically, neither one of those is going to work here, but then you switch to graphical or using a table to figure out the limit. And we figured out that the limit here was 1. L'Hopital's rule gives us a tool to analyze this analytically. Notice, again, I'm emphasizing this, there's no access point for this algebraically. I can't factor sine. Okay, so L'Hopital's rule gives us a way to analyze it. Let me give you L'Hopital's rule and then we'll come back to solving this problem. Okay? L'Hopital's rule says this. If we suppose that f of a equals g of a equals 0, some a, and f and x are continuous functions on the domain, then L'Hopital's rule, I guess I should say this, and f and g, so f and g are differentiable, also, g prime of x does not equal 0. Then we can say this. We can take the limit as x approaches a of f of x over g of x, and we can take the derivative of the top and the derivative of the bottom. Okay, so we can take the derivative of the top with respect to x, the derivative of the bottom with respect to x, and I'll get this, the limit as x approaches a of f prime of x over g prime of x. Okay. And that's what L'Hopital's rule says. It says if you have an indeterminate form, and the forms that we'll primarily be looking at are 0 over 0 and infinity over infinity, although it does apply to other forms. Other indeterminate forms, those are the ones we're concerned with. If you have that situation, then you can derive the top, you can derive the bottom, and then analyze the limit after doing so in the same way. So you try direct substitution and then algebraically if possible. Right? So this is another analytical tool. I'm not going to show you the proof for it, but it is in the textbook, and it's I think quite an interesting and semi-easily understood proof when you look at the geometry of it. It's quite a clever, not obvious result when you're given a limit problem that deriving is going to, given a limit problem that's a fraction, that deriving is going to lead you to someplace useful, meaningful, and correct. But it actually is the case. So I encourage you to take a look at that proof. It's going to take you 5 or 10 minutes probably to look at it and figure out what's going on there. I'm going to do a couple examples here, but I'm going to erase the board first. So let's analyze sine x over x, the limit as x approaches 0 of sine x over x. This was a limit that I told you should burn into your brain earlier in the year. And this limit, you might remember, equals 1. Okay, but let's see if we can use L'Hopital's rule to figure that out, because it does fit in an indeterminate form, 0 over 0 if you plug in 0. So if I take the derivative of the top and the bottom, then I get this. The limit as x approaches 0 Derivative of sine is cosine. Derivative of x is 1. Okay? So now I check, can I use direct substitution now? And I can, right? So now when I plug in 0, I'm going to get the limit, not the limit anymore, because we're evaluating the limit. I'm going to get just cosine of 0 over 1. And that's just 1 over 1, which is just 1. So L'Hopital's rule checks out with what we would see graphically if we look at the table. Let's look at this example here. We'll look at a different indeterminate form. So I've got secant over 1 plus tan. I'm looking at the limit as x approaches pi over 2. Each one of these functions, well, first of all, you figure out that if you just plug in pi over 2, you're going to get, each one of these is discontinuous at pi over 2. The numerator and the denominator, okay? So you take a look at the graphs of each. So in black, I have the graph of tangent. In brown-ish, I have the graph of secant. And I notice that as I take the left-hand limit, as we approach x from the left-hand side, both the secant and tangent go to positive infinity. As we approach pi over 2 from the right, both functions go to negative infinity. So what we need to do is analyze each each side of the limit, and then determine if each side goes to the same place, then we say the limit exists and it is that value. So let's check. We'll check the left-hand limit first. Not that it really matters. So we'll take the limit as x approaches pi over 2 from the left of secant over 1 plus tangent. And what you should do now is you should pause and see if you can analyze this using L'Hopital's rule to and get the answer. All right, so pause. Hopefully you've given that a try now. I'm going to take the derivative of the top, derivative of the bottom. What I'll get is the limit as x approaches pi over 2 from the left, secant tangent on top. Derivative of 1 is 0. Derivative of tangent is secant squared. Okay, so I can see that one of these secants or I've got a secant on top, and I've got a secant squared in the denominator, so secant over secant simplifies to 1, so I'll have just a secant on the bottom. Tangent is sine over cosine. Secant is 1 over cosine. So when I simplify those fractions, what I'll end up with is just the limit as x approaches pi over 2 from the left of sine. And that, now I can use, I've done some simplifying, I can use direct substitution, or plug in pi over 2. The sine of pi over 2, if you think about the unit circle, that's the vertical distance on the unit circle, that's going to be, at pi over 2 it's 90 degrees, so that will be 1, so I will get sine pi over 2, which is just 1. Right? I'm going to check the limit from the right now. So, by the way, I don't even think that I said this. From the left, or maybe I said this earlier. So from the left, they both go to positive infinity. So this was a infinity over infinity form, okay, indeterminate form. The AP test may ask you what indeterminate form is it. This would be infinity over infinity. Okay, so let's look at the limit as x approaches pi over 2 from the right of secant x, 1 plus tangent x. From the right-hand side, from the positive side, they're both going to negative infinity. So this is a negative infinity over negative infinity indeterminate form, and that's fine. That's still we can still use L'Hopital's rule, and so you can see that all of the algebra will be the same. I'll take the derivative, and it will simplify in the same way that the limit as x approaches pi over 2 from the left simplified, and you'll end up with the limit as x approaches pi over 2 from the right of secant x over 1 plus tangent x is equal to 1. Okay, so you can say that the limit overall is equal to 1. So there's an example of infinity over infinity. The last thing I will say is that sometimes you have to use L'Hopital's rule twice. I'm not going to give you an example of that because it's fairly straightforward. If you take the derivative one time and you still have infinity over infinity, or you still have 0 over 0, you still have an indeterminate form, then try L'Hopital's rule again. It's not always going to work the second time, or I'm sure we could build functions that the limit is can't be evaluated analytically no matter how many times you use L'Hopital's rule, but sometimes you just need to take the second derivative. And as long as your first derivatives are both differentiable, L'Hopital's rule still applies to the result. And that's it for L'Hopital's rule in indeterminate forms.